Good morning, everybody. We'll just wait until we go live. Well, good morning, everybody. Live from what is a snowy Ontario this morning, a snowy and cold one. Welcome to the second in our series hosted by the University of Waterloo's Multi-Scale Additive Manufacturing Laboratory, MSAM. This is where we're going to tell business stories where additive manufacturing either has played or will play an important part in the success. But the idea of the series is really the business is the star of the show, and additive manufacturing is definitely the supporting actor. We will be in the future taking a deeper dive in a different series of webinars into some of the research topics that MSAM specializes in. So if you're very deep in, if you want to be very deep in the weeds, I think today, I think we'll just encourage you to stay for those deeper dives in the future. So just while people come in, we'll just give it one more minute. We're very pleased today to have, I'll do my best here, Odilon Lemieux, the president and founder of Borrum Energy Solutions with us today. And he's going to talk to us about microgeneration. And we also have Issa Rishmawi on the line. He is one of our R&D specialists from MSAM to help with any technical questions, as I am definitely not a subject matter expert in binder jetting, although I do seem to find myself curiously drawn to anything that involves a propeller or a turbine. I guess that's being an aeronautical engineer at heart. When we come to questions, if you could put them in the chat, that would be great. But I would ask, could we have a name and an organization with the question, please? Because we may not be able to get to everything. It gives us a little bit of context so that we can get back to you. So a name and a question in the chat. I think Megan has posted a poll. We have Megan working in the background, who's one of our stars in the IT department. She should have posted a poll in the chat, which if you just like, whether you are from academia, whether you're a student, you're a researcher, whether you're from industry, whether you're in sales, that would give us an idea of the distribution. I'm not quite sure, Megan, how I see the results of the poll. Is it in the chat window?
It's in the Q&A.
It's in the Q&A. Okay, I'll pop that up. Perfect. Okay, so I can see we have, so if you're in the Q&A, we have 17 people who have liked that they're a student academia. We have 19 industry engineers. It's totting up all the time. Come on, guys, who's going to win this category? And we just have 2 people if you're sales or other. So that's great. So we've nearly got 50 people here. So I think we will look to kick this off right now. And we're going to open this with, those of you who know me know I'm a bit of a tease. So we're going to open this with a show reel that is short and sweet, hopefully paints a vivid picture of the subject we're going to talk about today. And of course, I'm going to leave you wanting more. That's what I always want to do. So Megan, could you please play our show reel for us? That's great. I'd just like to give a big shout out to the team at Borrum, to the team at MSAM, who helped with all of the clips there, and it'd be remiss of me not to say a huge thank you to Maria, who is just a second-year co-op student at Waterloo. She put all of that together. So that's a big shout out, I think, to the value in having a co-op student work for you, what they can do. And also, if you want to be featured in a future series here, then again, that's something that you get to take away from this, is something hopefully that is going to endure like that. So we're going to try and have a beginning, a middle, and an end to this webinar, and we're going to start at high level and gradually dive down. So I think probably, Odie, again, welcome. Thank you very much for being here today. The first question for you, your starter for 10. Could you tell us a little bit, what is microgeneration? Who's it for? What are the benefits? And you need to unmute yourself, sorry.
Okay, so good morning, Mark, thank you. And good morning to all our virtual people who join us. Microgeneration is a term that references the capability of producing electricity close to the point of consumption. Consumption could be your cottage, a tiny house, a dwelling in a remote communities or rural setting. Now, microgeneration can take the form of solar, can take the form of wind, can take the form of diesel with diesel generators. But the key thing here is very close to the point of consumption. Now, microgeneration is an up and coming, I guess, tool in the toolbox to help with the increasingly electrical costs across Canada, remote, as well as in some area reducing greenhouse emission. So let me expand on those two things for a second. If I take Ontario, where we live, the cost of electricity for those who are in the rural setting or cottage in rural setting, when you look at it, 86% of your total cost of electricity comes from distribution and transmission, and that's not going to change. And we know the electricity costs will keep going up. Okay, so whether you use solar or wind, microgeneration allows you to generate electricity close to, adjacent to your cottage or whatever, bypassing transmission and distribution. The unit cost of electricity is lower than what you pay to your local, to Hydro One, for example, in Ontario, and you save electricity. The other aspect of it is if we are in remote communities in Canada, and surprisingly, Canada has 300 plus remote communities. Those are communities that are not connected to any provincial or territorial grid. These territories, and there's about 280 of those, are powered by diesel generation. And the electricity cost is very high, plus it generates greenhouse emission. The use of microgeneration over there will reduce electricity costs and reduce greenhouse emission by lowering the demand on diesel generators.
Brilliant. So that's the pitch for microgeneration. It's electricity at source. It's going to reduce costs. It's going to reduce greenhouse gases. The specific way that Borrum generates electricity, maybe you could give us a sort of intro to wind power for homeowners. What's involved in a system, Odie?
Okay, so the Borrum is in the business of research and development and creating products related to microgeneration, wind energy generation. We focus on the wind. Now, the good news is Canada is blessed with some very good wind, so it's a natural resource, if we could call it that way. And so the fundamentals of wind turbine are fairly simple. The energy in the wind is a function of the wind speed, all right? That energy hits the blade of the turbine, in our case is 3 blades. The shape of the blade, when the wind hits it, makes it turn. As it turns, there's a shaft that connects to the generator. It is a generator that creates electricity. Now, if we want to go a bit further into that, the generator is composed of numerous elements, but the main two are the rotors and the stators. The rotors, as the name implies, rotates in unison with the blades. So as the blades speed up, the rotor rotates faster and faster with the blades. And then the stator is a fixed element in the generator. The secret sauce, if I use that word, is that as the rotor rotates within the stator, it generates electricity. Now, the challenge and the opportunity is how much of that wind energy can one convert to electricity? And there are two main factors for that. One is the blade design, and the generator. And the coupling, I call that, you need to optimize the coupling of these two to get a very good efficiency. Now, efficiency is important because as you create more energy, more electricity for a certain wind, then the customer is benefits from that because he gets more electricity, his unit cost goes down, and his payback is improving on that investment. So it's a win-win situation for everybody. At Borrum, we research and design and spend a lot of our investment on the design of the blade and the generator, because I believe that is where innovation will translate into business benefits and benefits to the end customer.
Great. So I guess it helps maybe that Canada is a little bit further north and maybe we're windier than some places. That's maybe one of the advantages that we have here in Canada. But I just said it's snowing outside today. So I'm sure there are some really unique challenges both with our climate and regulatory. Could you talk a little bit about how Borrum is addressing these challenges that are unique to our environment, Odie?
Absolutely. So like you said, the good news is Canada is blessed with good wind. We also have other challenges, right? So we are targeting anywhere to install a product anywhere in Canada, including the territories. So -50 is a design criteria for us, and we successfully tested at -50. There's also icing condition. There's also strong wind and all that. And Canadians are protected by numerous standards that we need to adhere to make sure that our solution is safe in any region of Canada. So we spend a constant amount of resources to make sure that we design the blades, the turbine, and the tower to meet those standards to ensure that our systems are safe in Canada to meet the harsh conditions that Canadians face on a regular basis, including maybe today with the snowstorm.
And presumably, you talked earlier about we have maybe 300 remote communities that you're looking to somehow you have to get this product out there and have to put it up. Could you speak a little bit about, you know, what was your model there for just ordering this off Amazon?
Well, I'm glad you're raising the question. Hopefully it won't create too many problems for us, but we borrowed, and I say borrowed, the IKEA model. So the idea here is that if we started this, we said if we can design a turbine and a tower that could be assembled by the end customer with tools that you find in the house, common tools, then two things happen. One is the end customer saves a lot on investment, and secondly, it's easy to maintain if maintain is required. So at the end of the day, we pre-assemble the turbine. Obviously, it's shipped with the tower and everything else, and within a day and a half, the customer can horizontally assemble the whole turbine and tower. And then you can use either a winch, electrical winch, a 4x4, an SUV, family car with a trailer hitch to bring it up. It's a tilt tower. And the value of that is you can bring it up, and when maintenance is required, you can by himself lower it, reducing his ongoing cost.
It's a fascinating combination of engineering design, the physics required, the aerodynamics, the electrical excellence. Really a more difficult problem that we often take these things for granted, I think. But it's been interesting. Can you tell us a little bit about how Borrum started using additive manufacturing in your journey?
Yeah, so very good question. So we do our R&D, focus R&D on the generator and the blades. The generator itself is made of two components I mentioned, stator and rotors. The design of the rotor plays a big role on the overall efficiency of the generator. Now, if you think about standard manufacturing, standard machining, there are some constraints in this kind of environment that if you want to limit the kind of design that we can dream of, that we can simulate and eventually produce. So the value here of 3D metal printing is to break those constraints and allows us to create some design that increase the efficiency of the generator, okay, that we wouldn't have with traditional machining. So here's an idea here. Here's an example of a 3D metal printing rotor. It's called an IPM. Long story short, the magnet goes inside. You can see a bit what it looks like here. There are some more complex shape, but the shape of it will be very difficult to produce with standard manufacturing, more so when the length of this thing increases, okay, and the tolerance. Right? So in a nutshell, from the rotor, increase efficiency from 3D metal printing parts, increase the energy production, increase the electrical, reduce the electrical cost for the customer, increase the savings and payback. So it has a very strong business benefit. The other thing we do, as I mentioned, is we do R&D on the blades. Now the blades are normally, the blades we have right now are 1 meter long. It requires a mold to be manufactured. So one thing we looked at is, can we create a prototype first to see, what they would look like and look at and test it to some extent. So we use another form of 3D printing. I think this is called a material jetting, if I understand right. So it is a smaller version of the blade. It's not 1 meter, but it has all the characteristic of the blade with the pitch and everything else that we can study before we commit to expensive mold and production. So those are two examples where we are using 3D printing to improve two things: shorten the cost of prototyping, and secondly, improve the cost benefit for the end customer.
Thanks. So just so I'm, and again, this is not for everybody on the line. This is not theory. This is a business owner, an entrepreneur saying, why did they use 3D printing? So this is not a theoretical lecture. This is a practical example. So we've got the buzzword is complexity for free, but you got to figure out what you're going to do with it. I think it'd be fair to say that in all of these series, all of the businesses are not going to reveal maybe any of their secret sauce. So we're really only getting a taste, I think, of what do we mean by freeing the geometric limitations of conventional machining, so we can have new shapes, we can have low volumes, with additive manufacturing. So Odi, you've used both. We've seen metal parts, plastic parts printed. How do you choose what process to use, what additive manufacturing process to use?
Well, it's a good question, and the short answer is I don't. I don't have the knowledge, the expertise, so I let the expert at MSAM decide which tools, which methodology, which process to use. And as a result of that, they're obviously the best expert to support that. One example that I want to talk about, and 3D metal printing is like a tool in a toolbox, right? When you want to produce products. In some elements, you do laser cutting. For some parts, you do CNC machining. Other parts, there'll be 3D metal printing. I'm not going to say it's the secret sauce for everything, but it certainly has a very good place in manufacturing and products, especially when you're constrained by design shapes and all that. One thing we're doing, I just want to talk about, I'm very excited about this, is I mentioned the stator. The stator, right now, we purchased the stator from China, nothing wrong with that. As a business, I've been trying to leverage the good manufacturing that we have in Canada, Ontario, and that's one part that we've not been able to do that. The reason for that is pretty straightforward. The stator is made on a material called silicone steel, and pretty much the only place, large manufacturer of silicone steel is China. Now, if you want to make your own stators and buy silicone steel as a material, it is very, very expensive. But if you go to China and say, what can you make stators with silicone steel? Suddenly they become very cost effective, all right? So as a result of that, our stators are made in China, and to be fair, they do a really good job at it. However, one thing that's exciting for me is there's a technology that MSAM and business are looking at, is how to use 3D metal printing to effectively create stators with the same characteristic as silicone steel. And in fact, by being able to play with the characteristic and the elements that make silicone steel, the hope over time is to create something that has better magnetic properties than the natural silicone steel you can get out of mineral resources. So the benefit to that would be, again, from a business, is to be able to produce more energy for your client. From an economic perspective in Canadian, is to reduce our dependence on a foreign country. And I think that what we learned out of COVID-19 a little bit is sometimes it's good to have some capabilities at home, not count on everybody else. So I'm very excited about that. It's fairly leading edge technology there. And obviously MSAM is leading the charge.
Brilliant. Okay, so again, just sort of summarizing. So the vision here is taking it one step further. Not only do we have the geometric freedom from 3D printing, but maybe we can get better material properties as well. So I think we're looking, whether we can develop a unique Canadian recipe for better magnetic materials. And with that, the specific technology that, again, Odi, I appreciate your candor in saying you're not the expert in choosing what the best technology is. And I think, I would say that's one of the big advantages working with a research operation like MSAM, where we have technologies across we have all of the additive technologies. We're agnostic, and we're also experts in applying them as well. So the specific technology that MSAM thinks is going to be the best to maybe exploit new magnetic material properties is binder jetting. So, as promised, let's give Odi a break here. So that I think I've got a couple more questions afterwards, and then we'll please, in the audience, put your questions into I think I said the chat earlier or the Q&A. I'll look in both places. But let's take a deeper dive right now into binder jetting. Again, a huge thanks to the team at MSAM for shooting this video. So this is 100% produced by MSAM. We're not using a manufacturer's video. And again, Maria put this all together. So Megan, if you could take us into a deep dive on binder jetting, thanks.
At the core, additive manufacturing is the process of joining units of materials to make parts from 3D model data, usually layer upon layer. Designs come to life in front of the machine operator. Binder jetting is an additive manufacturing technology which uses powders as raw material. The powder materials can be metal, ceramics, or polymers. These systems work well even with highly irregular powder morphologies. This makes binder jetting a highly versatile manufacturing process. It also has unique advantages such as scalability, a wide range of material compatibility, and the ability to vary material properties in different locations of a single printed part, all of which can be leveraged in industrial and biomedical applications. In binder jetting additive manufacturing, the principle behind part fabrication relies on the sequential spreading of thin layers of powder, which is done using a roller, where a typical layer of thickness is in the range of 50 microns. This is followed by selective jetting of a liquid binder or glue using a printhead. The printhead jets the binder at the location corresponding to the part slice being printed. This process is repeated until the final geometry is complete. Now that we know the principle behind binder jetting, let's take a closer look at the binder jetting additive manufacturing workflow. The first step is component design, which is done in computer-aided design environments. Once the designs are completed, they are transferred to the binder jetting machine for its so-called green part manufacturing. Here, the part orientation and custom process parameters are programmed, and other parts are produced in a layer-by-layer fashion. It is often necessary to iterate and optimize process parameters to improve geometric fidelity and green part density. Parts in this state are between 50 to 65% dense. Once the green parts are manufactured, the binder or glue is cured by exposure to heat, either inside the machine or in a curing oven, and the parts are depowdered and cleaned. The most complex part of the binder jetting process are the heat treatments. For binder jetting of metals and ceramics, heat treatments at high temperatures allow for powder particles to fuse together and for the material system to densify. Typical final densities range from 85 to 95%. In binder jetting, due to the heat treatment and densification process, distortion may occur. It is common that binder jetting components undergo post-processing steps, such as media blasting, machining, and infiltration. Let's take a closer look at each step. Digital file manipulation, part orientation, and process parameter setup. Each material and design will have its own optimized process parameter library. The machine operator, depending on the material type, can load powders into a hopper system to dispense powders onto the build platform, or the operator can manually fill a feeding bed mechanism with raw materials as shown here. Here we see an example of a machine modification to allow work with smaller quantities of powders. The build platform can be large, almost 0.5 meters, or small, a few centimeters. Here, we see the previous layer being heated to cure the binder before a new layer of powder is spread. Then, the powder is dispensed from a hopper system at the top onto the build area where a roller spreads it uniformly across the layer. Finally, the printhead jets the binder to create the part layer. There are multiple steps to part heat treatments. The first step is binder curing. Here, we see parts going into the curing oven to finish hardening the binder or glue and allow for the part to be strong enough to be handled during depowdering. The parts can be placed back in the machine after curing to depowder. Once the parts are strong enough to be handled, they are depowdered and cleaned. The most complex set of steps in the binder jetting workflow are the heat treatments. A heat treatment needs to carefully orchestrate the time sequence of ramp up and ramp down temperatures, as well as the environment gases to achieve controlled part densification with minimal part distortion and desired material properties. Specifically, the sintering process is quite complex if we are interested in customizing both the densification behavior to control the geometric fidelity as well as material properties. For soft magnetic materials, for instance, the MSEM Binder Jetting Research Group have developed densification models to predict the shrinkage during sintering and determine geometric compensation factors to obtain shape fidelity, and are in the process of developing specialized heat treatment schedules to attain specific magnetic material properties. The ability to control the heat treatment schedule during densification is unique to the binder jetting additive manufacturing process and shows promise in manufacturing generator components. We hope that additive manufacturing technologies, and binder jetting in particular, will provide competitive advantages in the energy sector, specifically for small-scale power generation.
Brilliant. Again, thanks very much to the team at MSAM for shooting all of that video and for Maria for putting it together. So my take on that is there's a lot going on. It's a multi-step process. Maybe there's a little bit of a sting in the tail in terms of the heat treatments and getting that right. I think there's a lot to be considered: the right powder, the right characteristics, the right density. How do we control the geometry? How do we get the desired magnetic response? So it seems like there's a lot of promise, maybe a broader universe of materials. And of course, we've got the no tooling cost advantage that typically comes with additive. So, you know, we've got the no tooling cost, we've got geometric freedom, maybe we've got material freedom. So we really open that up for the design space, and economic promise as well with binder jetting, I think, in terms of the speed of droplet spraying. So if we can find the Goldilocks recipes using science, not trial and error, we should be well set. Or put another way, if you're a scientist, a statistician, experimentalist, this is truly a multivariable optimization because it's a lot more complicated than we made it look there. And as I say, this is just an intro series. So before we answer some of the questions that have come in from the audience, and thank you for that, please put your questions in the Q&A. We'll try and get to them. I just want to ask Odie one of the questions that I should have asked at the beginning, but you know, can you just tell us, Odie, why did you start a business here in Canada?
Yeah, that's a good question. So first, well, I'm a proud Canadian, born in Quebec, Montreal, where I did my electrical engineering studies, moved to Ontario, where I raised a family, and worked for a decade or so with Ontario Hydro. So I got some background there, okay? Looking at trends for clean energy, greenhouse emission, we all know about that. I was looking at solar panels and realized they were pretty much all done mostly in foreign countries. Very little opportunity for innovation without basic research. Then I look at wind turbines, and we have the large ones that are made in Europe. Very difficult to compete against that right now, right? But then I realized something that's very important, is that in any electrical grid, there's a cap, if you want to, a percentage cap ceiling on the amount of renewable energy that can be injected in the electrical grid. And that's because of the variability of wind and solar. Difficult to predict Mother Nature, difficult to predict the sun, difficult to predict the wind. So renewable energy at the grid level fluctuates quite a bit. And it's been shown that beyond a certain percentage, those grids will become unstable. So eventually, as we add more solar farms, as we add more wind farms, we're going to reach that threshold. And the next step to increase our electricity clean energy generation will have to be microgeneration because it is close to the end customer and does not attach to the grid. Now, having said that, when I look at Canada and I look at the microgeneration wind turbine available in the market, very few were built to sustain the harsh climate of Canada. And so I thought, okay, this is a business opportunity. This is a problem that needs to be solved. And more importantly, I wanted to leverage the very good education system that we have in Canada. We produce great engineers, and we also have great manufacturing capabilities. And I'm quite proud right now to say that over 80% of all the parts of our turbine and tower are made 100% designed in Canada, 80+% manufactured in Canada. And over last year, I was able to bring back some parts made in Asia back to Canada. So I'm working on that, and I believe that it's a win-win situation.
And it would be an overstatement to say Borrum is powered by Waterloo, but you also you hire co-op students. You have some of the research feeds into application as well, doesn't it? I think that Borrum has already got some Waterloo alumni working for you.
Well, you know, the proximity. So University of Waterloo, we co-op students, Wilfrid Laurier co-op students. We have some from McMaster as well and Guelph. One of our engineers comes from another university in Quebec, so we don't discriminate. I think there's great opportunities, but certainly from a co-op perspective and the research capability in University of Waterloo, in this case MSAM, are fantastic. If you look at the world, they are on the top of the world for the research capabilities there. So it's only an advantage for us.
So let's just one last question for you. You've been working with MSAM now for a few years. You know, where do you see that relationship going in the future?
Well, the relationship will continue to grow. It's a great example of university industrial partnership research. So it's a research that has some clear, tangible benefits, practical benefits. For us at BES, it's a source of innovation. All good things will be copied over time. So the Anora, our turbine right now, will be copied eventually. We have new innovation coming in, but the research provides us, and the interaction with the research center gives us opportunity for more innovation as we move forward. I think it's good for the university, it's good for Canada, it's good for climate change, and also helps our customers reduce the electricity costs. So I'm very excited about our future, both at university, the research partnership, and for Canada as a whole.
Brilliant. Okay, I'm going to, we've got some questions that are more technical on binder jetting, but before we get to that, I've got a question here from Rafat, who's with Seafur Technologies. He's talking about wind speed varying with the height above the ground, and how do you address this in terms of the market for microgeneration wind turbines?
Good question. So our standard turbine tower height is 6 to 6 feet, and we can model that. We have the capabilities to model the wind profile of any location in Canada with support from Environment Canada data. We also have the knowledge and technology to be able to figure out what that wind speed will be at lower height, 44 or 22. And from that, we can predict what the annual energy production will be for a specific location and turbine height.
Brilliant. Okay. So there's a question that it's from Nigel from Nergica, who's had to leave, but I think it's a great question, so we should answer it. And he's saying, how do you deal with after sales issues for remote communities? And you know, he's heard with no evidence to support it that sometimes, you know, they're left to themselves after something is installed. Presumably that's something that Borrum is working very hard to make sure your product is reliable. You know, how do you provide support to customers in remote communities, Odie?
Yeah, good question. So first of all, we have no electronics on the turbine. Okay, as I said to my engineers last year, if you have a circuit board problem in Cambridge Bay or Arctic or Wellert, tough to find somebody that can fix it, right? So we have no electronics. Second, everything is mechanical, and everything can be either replaced or fixed, just like you do with skidoos and ATV with the wrench and things like that. So thirdly, it's very simple. Contrary to large turbines, we don't have transmission. There's no lubrication system, and even our furling system does not have any spring or anything like that. It relies on gravity. And if we lose gravity, we have bigger problems than just wind turbines.
Thanks, Odie. So I am going to, since Issa joined us today on the line, I asserted earlier that maybe binder jetting was going to increase the universe of materials. And certainly I come from the world of laser powder bed, and we're trying to increase that universe, but it's a tough road to hoe. So Issa, would it be fair to say that can any metal or ceramic be processed using binder jetting?
Hi, Mark. Yeah, that's a good question. So the short answer is yes. The process is very forgiving. Essentially, as long as you can glue whatever material together, you can manufacture with binder jetting. So you can also print polymers, by the way, so not just ceramics and metals, but also polymers. We have successfully printed biocompatible polysiloxanes in our research at MSAM. Now, part of the challenge, of course, with any material that you print is that you need to sinter it. Usually this isn't an issue. For more exotic materials, we would need special conditions, such as high pressure or very high temperatures. So one example of that would be tungsten carbides or silicon carbides, which are very hard materials. Current research in binder jetting is also pushing the limits of the binder material. So with ideas to use things like metal ink binders or nanoparticle suspension binders in order to create stronger parts right out of the printer. So we can expect the technology to improve even beyond what it is today, and find more and more industrial and biomedical applications where it can be used.
Awesome. I think that's great news for the audience. Again, if you have a question, put it in the Q&A. So I'm going to follow up on that one. In the video, we saw some cylinders that maybe looked less precise than I might have expected. But could you talk a little bit about geometry and distortion and the challenges and the bright future ahead?
Certainly, yeah. So I should clarify that some of the cylinders that you might have seen cylinders that looked a little not too geometrically precise, and others that looked really precise. There was a cube and a tension bar that looked really precise. So those that were a little bit not too geometrically precise were printed on a 15-year-old binder jetting machine. That's one of our older machines that we have at our group, and so what I'm trying to say is that, you know, as the technology improves over time, and especially in modern technologies, modern machines of binder jetting, they have very high resolution, both on the printing side in terms of the print head and how small the droplet size is and how accurate it is to print a part, but also in the mechanics of the printing itself. We can get very geometrically accurate parts. So modern machines, you can get resolutions of 100 micrometers or less, even 50 micrometers. Sometimes you might see it on the machines. Now, so that's on one part. So getting the green parts with very good geometrical fidelity is one thing. And you mentioned the other thing was that distortion and sintering. So that comes in with most of the applications you'd need to sinter. And so the question of there's shrinkage. So shrinkage is normal, and we expect the parts to shrink. And typically we would, this is something that we can control and we can plan ahead for. Usually we would characterize it and with either, you know, in 3 dimensions or in complex shape tests that we do, and so it's very predictable. Now the second part is distortion, as we mentioned in the video, one of the ways that we try to kind of overcome the risk of distortion is through modeling. So we try to predict how the part might distort, how it might behave when we add heat to it. And another way is through relying on the existing foundation of knowledge in the manufacturing techniques of powder metallurgy and metal injection molding. So these technologies have been in place for decades, and we're certainly building on that. So we're standing on the shoulders of giants here with binder jetting.
Thanks.
Yeah.
Okay. And hopefully that answered a question from Alex Ellery. Hi, Alex, from Carlton, who wants to build motors on the moon. So we certainly do need to stand on the shoulders of giants to do that. But it's the sintering process that increases the density from the green part of 50-odd% to 85% plus. I think that Issa was talking about there.
Yeah,
cool.
and I just wanted to mention this. So 85 is in these days, it's a kind of conservative estimate. We can push densification up to 99 or above 100%, only like without further infiltration. We can push the boundaries of the sintering, and of course it would shrink quite a bit. But as I said, that's predictable. So yeah.
Excellent. So I'm going to ask, I had a question for Odie. You talked, what happens when it gets really windy? I think you alluded to this, I guess, from memory. What is it? Kinetic energy is V squared, isn't it? And then so multiplied by V, so power goes as V cubed or something like that. So I guess at some point you would either generate an insane amount of power and everything would get very hot, or you need to decide to derate the system. So how do you do that, Odie? You talked about no springs. So how is it simple like that when it gets very windy?
Yeah, so good question. So we decided not to have any electronics. So the system, to make sure that the turbine and the blades don't go beyond a certain RPM speed, rotational speed, is called a furling system. And it's 100% mechanical and very simple. And what it does is that it's designed so that at a certain wind speed, the blades will be moved away slowly from the direction of the wind. But they will still rotate and they will still generate electricity to a certain point. And then when we reach a very high wind speed, then the blades are pretty much at 90 degrees from the wind direction. And
so is that a bit like if you're sailing, you bring the boat head to wind to sort of depower the sail sort of thing? Okay.
Very, very similar fashion. The challenge there is in your example, you got salesmen that can, sell people that can do that. In Northern Canada, remote communities, nobody's going to stand there in case of. So it's a mechanical system that is designed to leverage the power of gravity that we have on Earth. And so there's no springs, there's nothing I can break. And as I said, as long as gravity is still present, it will be working.
Brilliant. So I think I'm just going to have one more question. A couple of questions I think we probably can't answer today. There's one from Sheng Yang at Guelph on how do we choose the sweet spot for additive manufacturing. I think that's something for a future discussion. I don't think we're going to get into that today. It's a great question. And one from Frank DeFalco. He's asking Odie, is this only for remote use? Should somebody put one of your systems in an urban area? What would you say to that?
Yeah, that's a very good question. At this present time, we're targeting a rural setting. That's because the wind is more stable in rural setting. Let me explain that a little bit. In urban setting, you have wind, but you also have a lot of buildings, all right? And those buildings create turbulence. And if there's something that turbines don't do very well is with high turbulence wind. When the wind shifts direction up and down, left and right, the efficiency of the turbine drastically is reduced. So having said that, one option is to go very high above all the buildings in your urban setting. That may be an option. We haven't looked at that. But other than that, I would say the critical factor for urban setting is wind turbulence.
Thank you very much. We've got some uber technical questions from Will Sparling. This one is going to be for ISA Live, so we're really going to put him on the spot, but here we go. This is Will's from UBC. He's a PhD student, and he's asking, high performance magnetic properties are often associated with your control over crystallographic orientation. Do we have a method for crystallographic orientation in binder jetting, or are we focused, is it predominantly on the composition to improve magnetic properties? And I guess if I decode that for a second, I think he's sort of saying, is it the input powder that's important, or is it the or what you do afterwards that determines the magnetic properties? I guess the answer is going to be both, but over to you.
Yeah, so that's a good question. So in this specific project, our focus is first on the sintering aspect and how we play with that to improve the magnetic properties. Now, generally speaking, in binder jetting, it's both, right? So we have to pay attention to both, and so it's a very fair question, because that often comes up in the final stages. You know, once you've successfully printed whatever you want to print, and geometrically looks great, and it's you've sintered and without any issues and distortion. But then, all right, now it's mechanical or magnetic performance. How does that affected by the powder material itself? So there's often some planning ahead and refinement in terms of what powder material to use, and some material science that is involved in both the sintering aspect and also the powder selection. Yeah.
And I guess one thing that I'm drinking from this at least 7 fire hydrants of knowledge through all of the universities we're associated with. But one of the key things I think is when we put heat into the system is very different with binder jetting. So with laser and electron beam, we're putting the energy into the powder bed itself. With binder jetting, it's almost a room temperature process to begin with, and then later on we're adding the heat. So there's a key difference there just to bear in mind. I'm not saying it makes it any easier, but it's just different, isn't it? A question from Kyle Egedy is, would hipping, hot isostatic pressing, is that something? It's often associated with laser powder bed that we would do that. Is that a process that's used to increase density, or is it just a fantastic process to increase cost? He says cynically.
Yeah, so absolutely it can be used to increase density. Past, I would say, if we can sinter up to 92%-ish density, then we can just hip right after that. And certainly beyond 95% for sure, yeah. Great,
okay, look, I think we've pretty well answered all the questions. We've answered the what'll she do, Mr. Actually, what will she do, Mr. Odie? What kind of power are your systems rated for? Before we'll finish by just playing the show reel again and then close out. But could you just tell us the power that you get and maybe an idea on the payback for this before we play the show reel and say goodbye to everyone? You're muted, I think, Odie.
Okay, thank you. Yeah, good question. So the Anora turbine has been released to market, is rated at 1.2 kilowatt at 11 meters per second wind. Depending on your location, this turbine can generate between 1 and 3 megawatt of power a year. All right. Now, again, that's based on your location and the wind profile. And then the payback, depending on of your wind profile and how much you pay for electricity, we have some location that's below 5. Most of them are below 10. And I think
5 years.
5 years, yeah,
okay.
Below 10. If you look at comparable like solar panels, for example, it's probably much higher. The reason for that is solar panels are very efficient when the sun hits them at 90 degrees. As you move north, solar panels efficiency goes down. but the wind is more better for wind turbines. So at the end, what I said is I think a joint system of solar and wind is probably what's going to win the day.
I always love a hybrid solution. It seems balance is often results from that. So let me just thank you so much, Odi, for being our guest today. A fascinating insight into the challenges facing a business, what you're trying to do. Just really appreciate your insights, and thank you to Issa as well for fielding the technical questions. I hope we answered the audience's questions. And Megan, maybe you could just play us out with the show reel one more time, and we'll look forward to seeing you in a few weeks. Cheers. Thank you, Megan. I think you can take us off air now.